So two things are that we are interested in. One is the stiffness or the elastic response. If I apply a load, how much strain or how much deformation do I get? And the second thing is, if I apply a load, when does my structure fail? So as far as the first part, the so-called elastic response, if you have isotropic materials, then you only need two elastic constants, any two of these three. E, Young's modulus, G, the shear modulus, and nu, the Poisson's ratio. And as you well know, for isotropic materials, this is the relationship between the three of them, so any two are enough to define the others. Now, if I have anisotropic materials, then instead of two, I may need as many as 21 completely independent. Why are they 21? Because in general, I have 6 stresses and 6 strains. I'm going to use matrix notation just because it's a little easier. We have 6 stresses and 6 strains. So if I'm going to relate those, then I will have a 6 by 6 matrix here. Is there enough room? E13, E14, E15, E16. And it's a symmetric matrix. So if it's a 6 by 6, and you calculate the terms that are the same because of symmetry, then you are left with 21. Conceivably, above the diagonal, including the diagonal and everything else, there's 21 terms that they could be independent of each other. It so happens that most materials that we use don't have to fall into this category, which is very difficult to characterize. Just the number of tests that you would need, for example, to get these 21 stiffness values would take forever. But it so happens that there's a class of materials, the so-called orthotropic materials, for which 4 elastic constants are more than enough. Basically, there's the stiffness, as called here EX, stiffness in a certain direction X. Then perpendicular to that, there will be a different stiffness EY. There's a shear modulus and a corresponding Poisson's ratio. So that's the stiffness story. Now for failure, in metals, everything starts with yielding, and that's very nice. All metals will, just about all metals will yield to some amount, and that's reasonably well understood. Basically, we have plastic deformations, and you can go from there in the post-yielding final failure collapse in a relatively well-defined situation where we understand what's going on in the material. In composites, because we have 2 components, that's why they are called composites, there's at least 2 components, the matrix and the fiber, we have a whole bunch of things that can happen, and there's even no guarantee what happens first and what happens next, or how they interact. The matrix may yield, the matrix will eventually crack. You may have delamination, which is separation between layers. Remember, we are putting together different layers of this orthotropic material that we will call eventually a composite to make a laminate. So between the layers, we can have delamination. Those of you with me in the second part of the course in the 4th quarter will see a lot about delamination. We can crack or break the fibers, or we can crack or break the interface between fibers and matrix, which is completely different than the fiber and the matrix. So all these usually to some extent happen, and they interact, and it's a nightmare to find out what's going on. So composites are inherently much more complex. The irony is, because they are so complex, we tend to simplify them so much that they sometimes are even simpler than metals. But of course, this kind of simplification leads to approximations that are acceptable part of the time, but definitely not all the time. If you look at a composite and start from the basic constituent and start going up, you will see that down in the micron level, we have a single fiber, and on the surface of that single fiber, there may be some defects, some tiny cracks or scratches, or maybe even inside the fiber, but we can't see it most of the time. If I now go a little larger in scale, and I look what happens on 3 different layers. Here we have 3 different layers. This one to the left of the white region, or the white-gray region, this one is a minus 45 ply. We'll talk about directions and orientations much more later on. The one in the middle is 0. So essentially the fibers in the middle are running along the length of the photograph shown there. That's why it has completely different color. And then we have again minus 45 on the other side. Basically the little dots that you see are the actual fibers coming at us. So under some kind of loading, you can crack the matrix. And when you crack the matrix, the crack goes in between the fibers at the beginning. You cannot break the fibers. They are much stronger. So if you're a crack and you're trying to move around, you will select the path of least resistance, which means you will zigzag a little bit. That's why it's not a perfect straight crack. And you hit an interface between the minus 45 in this case and the 0, or in this case the 0 and the minus 45 on the other side. And then as a crack you have to decide, do I stop or do I continue? And if you are a strong crack, then you will try to move into the 0, and sometimes you can do it. Otherwise you will move along the interface. Basically, as soon as you reach, as a matrix crack reaches a layer or a ply with fibers in a completely different orientation to the fibers in the ply from which it was coming from, it now becomes extremely difficult to crack those fibers, and therefore you select to turn around. That means now the crack moves between the 2 layers, and it becomes what's called a delamination. Now you can combine these excuse me, as you go to an even larger structure, and you will see now a whole bunch of delaminations in a composite plate which was about 1 centimeter thick under impact. This was impacted, and which is one of the major threats for composite structures. So you get these kinds of delaminations that are much more pronounced now, and many more of them through the thickness. And you also get, if the lighting permits, between the delaminations you can see there are actually cracked entire plies, which means that you also have some broken fibers. And finally you go one step beyond in the size. Now you are in the centimeter level, where this is actually the face sheet of a sandwich tested in compression, and you see how it failed, where you had this bulging out or small half wave of the face sheet pulling away from the core and breaking in compression. It's the so-called wrinkling failure. So there are different failures or different combinations of failures at different scales, and there is a big decision that one has to make. What level am I modeling these? If you are a person with infinite computer power and with physics background, you can start way down here or even smaller, talking about the molecular or even atomic level, and try to then go from that, integrate up as you go in scales. I don't think there's enough computer power and knowledge even at this point to be able to start at such a lower level, even though eventually we have to start moving down in that level. Typically you back out and you say, I admit defeat. I will start with a building block that will be the layer itself or the ply, and I will characterize failure at that level, even though in reality there are all kinds of mechanisms that happen at even smaller levels. I will characterize it at that level, and based on what I know at that level, I will try to predict what happens at the full-scale level. And usually you fail miserably because it's not as simple, it's quite complicated, and we don't understand much, and we'll talk about that, about failure criteria, but that's the best we can do today. So keep in mind that the problem itself is complex. The mathematics and the physics are very complex. The computational power can be quite prohibitive. Progress has been made in many respects, and we are understanding some of these failures better than before. But we have to make approximations. In fact, the whole course is about making approximations. So let me open a parenthesis here. I was going to go for an interview at a company in the US. And usually you try to find as much, if you're going to go for an interview, you better find as much as you can about the company, what they do. I mean, you're not just going there because they have a big name. You want to go there because they do interesting things. So I found out about some of the people that were working at that company, and one person that I knew said, you had better be prepared for some difficult questions. So like what? I said, I know my math and everything. Oh, the math is the last 5 hours. Don't worry about that. It's what is, which is true. The last 5 hours I was doing math. The first question they will ask you is, what makes a good engineer? And if you answer that well, then it's going to be much easier. If you don't answer it well, you have to make up that problem. So anybody knows what makes a good engineer? So we might as well say it out loud, man.
Making the right assumptions.
Exactly. A good engineer can, presumably, in a piece of paper, in fact, the usual story is on napkins. You write, you scribble something and it's within 30% because you know which assumptions to make to simplify the real structure. So that's the whole course here. Will be making a whole bunch of assumptions, some of which will be quite arbitrary because it's convenient, but many of them will be actually based on a realistic understanding of what the structure does. And your final project will have a lot to do with you guys making the right assumptions on your own. You can ask me anytime for homework or the final project. You can come to my office or during lecture or whatever. But after a while, I will be leaving it up to you to make the right assumptions. So the orthotropic materials are the ones that have two planes of symmetry. So if I make a section cut in a typical composite, in fact, this is showing two layers, and I draw a vertical line here and a horizontal line there. Now, other than this relatively clearly well-defined resin layer, which is the resin layer between the two plies, it's very difficult for you to tell whether you are on the left or on the right-hand side, in the sense that there appears to be symmetry with respect to this vertical plane perpendicular to the page and this one, or the horizontal plane. So if there are these two axes of symmetry or planes of symmetry, then the analysis, the modeling simplified tremendously. Those 21 unknowns become only 4, the 21 stiffnesses. Of course, as you can even tell from this scale at which I have the picture, there is no such thing as perfect symmetry, and the smaller or the more you zoom into the structure as shown here at the bottom right, the more asymmetric it becomes. So depending on what level you are modeling, whether your symmetry holds or doesn't hold becomes a big deal. If you're trying to model the structure, and as I said, we select arbitrarily to go to the level of a ply. The ply is the one layer of fibers and matrix. And that's our starting point. You could go further down or zoom further in, but as I said, becomes computationally very expensive and very difficult to understand what we're doing. So we're going to start at a ply. And the ply consists from fibers and matrix. One example is where you have unidirectional fibers, so it's a unidirectional tape in this matrix that make this kind of a ply. And the approach, an ideal approach, would be I characterize the fibers, I know their properties, stiffness and strength. I characterize the matrix, I know its properties, stiffness and strength. I put them together, and if I know what I'm doing, I should be able to predict the properties, stiffness and strength of a ply. Turns out it's reasonably successful when it comes to stiffness. It's miserably failing when it comes to strength. There's certain things about the mechanisms of failure that are not easily understood on the basis of what causes a fiber to fail and what causes a matrix to fail individually. When you put them together, that interface and how they interact becomes a little difficult to understand. So you can say, okay, I have my micromechanics, which I can use when I'm comfortable with, but I recognize that that might be limited. And I can then say, okay, let me just take a single ply with the fibers in it and characterize that. By characterize, I mean let me do my stiffness and strength tests, and on the basis of that try now to build up an entire laminate and its own properties. And this is the level which we will be dealing with mostly in this course. So when I stack them together, I get what's called a laminate. So I can take plies or lamina, one lamina, plural laminae. There's the extent of my Latin. And we get a laminate. Now the laminate has three axes, of course, X, Y, Z. And it has forces and moments that we will be talking about some more in a little bit. But those forces and moments will cause deformations. The question for us is, if I know how a single ply behaves, how can I now determine how the stacked up set of plies or laminates